Everyone, I hope you're well. Today we will be talking about a very important Leetcode problem called twosome. It is simple, easy, yet crucial to understand because it will help us learn more about data structures and how we can leverage them to reduce the time complexity and make our algorithm faster. So let's jump to the problem description. We have given an array of integers, nums, and an integer target. Return indices of the two numbers such that they add up to the target. Pretty straightforward and simple. So we're looking for two numbers, A and B, and sum of this two number should be equal to target. You may assume that each input has exactly one solution and you may not use the same element twice. Okay, we have some more information that we will find exactly one solution and we cannot use the same element twice. I'll explain what it means later, but for now, what we can understand is we cannot use, if number two has appeared just once, we can only use it once, we cannot use it twice. You can return the answer in any order, so order of those indices doesn't matter, we can switch them. Okay, so now let's talk about the solution of this problem. What I can say here is from A plus B equals to target, there should be a B which is equals to target minus A. And in the example that I have taken, I can say I'm looking for a B which is 2 minus a number A. So what I can think of is to iterate over this array nums and substitute the value of A to get the complement B, right? For every A, we will get the complement B, and we will check if the complement B exists in this array or not. If it does, then we have those two numbers A and B. If it is not, then we will move on to another number and do the same thing. So let me briefly walk you through this. What do I mean by it? So let's start with the number 7. And I can say for number 7, B is equals to 2 minus 7, which is what? Minus 5. Does minus 5 exist in this array? No. So we will move to another number. For another number, B would be 2 minus of minus 3, which will give us 2 plus 3, 5. Does 5 exist in this integer array nums? Yes, it does. So we have our solution and we will return the indices of both the numbers, which is like in this case 0, 1, 2. So 1 and 2. So that will be our solution. Perfect. So now let's talk about the time complexity of this problem. So what we did here is we have a for loop, not for loop. It's a for loop. Okay. So we have a for loop for n items. In the worst case, we will end up iterating over all the n items. And for each of those, what we are doing is we are trying to find the complement B. So again, what we will do is we will run another for loop for this n items and we will check if they are equal to B. So what I can see here is a nested for loop. So again, if we calculate the big O or the time complexity, it's gonna give us n for this and okay, what is this? Okay, n for this and n for this internal loop. So what will be my final time complexity? It will be big of n into n, which is big of n square. So quadratic time complexities usually are not preferred because they are very time consuming and they take a lot of power, programming and computing power. So we often try to find an efficient solution, and in this case, we are going to do the same thing. So my question is, can we make it better? And the answer is yes, we can make it better. How about we try to reduce the time required to find this number B? So into the inner loop. So right now we are taking big of n to iterate through the array and see if the number B exists or not. So one way we can do is to apply the binary search, but binary search only works into the sorted arrays. And to sort this array, it's going to take another computational power. So the time complexity will be higher than log n definitely. But another drawback of sorting this is we have to keep the track of original indices that we are given. And sorting this will shuffle the indices of the elements, and it would become another challenge to keep the track of original indices. So we will skip that right now. And but my question is, can we still do better? And the answer is, of course, yes, we can do better. How about we bring in some data structure where accessing this key is efficient than big of n? So I can think of hash tables, and you can access these elements in hash tables in the constant time, which is just big of 1. And what I can do is I can look for the keys in my hash table. If they exist, I can retrieve their indices and then print it or return it to the server. Okay. So let me iterate you through how it's going to work. So for example, if we start with the number 7, again, for number 7, we have this b, which is -5. So I'm going to go and check into my hash table. Does -5 exist in my hash table? No, because I just started. It's empty. So it does not exist. So what I'm going to do is I'm going to I'm going to put 7 and the index of 7 in my hash table so that later on if I'm trying to access this number 7, I know where it is. I know the index of this 7. Okay, let's go to another number, which is -3. So b is equals to 5 for -3. So I'm going to look for 5 in my hash table. Does 5 exist in my hash table? No. So what I'm going to do, I'm going to add -3 in my hash table, indices of -3, which is index of -3, which is 1, and then move on to the next element. I'm going to do the same thing for 5. So what would be the b for 5? So 2 minus 5, it would be -3. I'm going to check if -3 exists in my hash table. Yes, it does. So what I can do is I can get the indices of -3, and I already have the indices of index of 5 because I'm iterating in an array and I'm keeping the track of index of the current element. So what I can do is I can return the index of 5, which is what? 2, and the index of -3 that we have is 1. So that would be our answer. Since the order does not matter, we can return the answer in any order. 1 comma 2 is fine and 2 comma 1 is also fine. Okay, let's talk about the time complexity again. So what we did here is we are iterating through the array. So we're using a for loop on n items, right? And for each item, we're looking up b, if b exists or not. And what is the computational requirement for looking up for b is big of 1. So for every n items, we are using big of 1. So the final complexity will be n into 1, and it will be big of n, which is much, much, much smaller than big of n square. And this is what we want. This is what we were working for. So I hope you understood the solution, and I will be posting a code for this too. Stay tuned. Thank you.